We generally think that electric fields do not affect neutral objects. In the gross sense, this is usually true enough. However, sometimes the details matter. Most neutral objects are composed of charged particles, with some exceptions, such as neutrinos or photons. However, if you do have a neutral object that is made of charged particles, an applied electric field can affect those charged particles and, in some way, affect the object as a whole. One way of doing this is by inducing a dipole moment in the object. So take, for example, a neutrally charged atom. This atom can be described as a positively charged proton or positively charged nucleus surrounded by a negatively charged electron shell. Under normal circumstances, the nucleus and the shell are in the same location, and their charges cancel out completely. However, if you apply an electric field to this atom, the positively charged nucleus will be pushed in the direction of the electric field, and the electron cloud will be pushed in the opposite direction to the electric field. These two charges will experience a slight displacement and will therefore create a dipole. So a dipole, often modeled as in this picture here, is made of two charged objects with equal magnitude charges and opposite sign charges slightly displaced. We can describe a dipole object by the dipole moment, in this formula represented by the letter P, is equal to Q, that is the magnitude of either of these charges. Again, the net charge of the object is going to be 0, so Q is the magnitude of just one of these charges, times D, where D is a vector that goes from the negatively charged object and points towards the positively charged object. For atoms and molecules, we can say that the induced dipole moment is equal to this quantity alpha, which is called the polarizability, times the electric field. Now, in general, polarizability is a tensor, which means that it has 9 components, an xx, xy, xz, etc. And its relationship is described in equation 4.3 of your textbook. Now, we can simplify that. If we can determine the eigenvectors of the molecule, then we can reduce alpha into a diagonal tensor, meaning it has an xx term, a yy term, a zz term, and all the other terms are 0. Furthermore, if we are dealing with a spherically symmetric object, such as a lone atom, then the xx, yy, and zz terms are all equal to each other, and alpha essentially becomes a scalar. Some molecules have a dipole moment built into them. The example usually used is water. Water, H2O, is 2 hydrogen atoms covalently bonded to an oxygen atom. Now, this oxygen atom has 8 protons, and normally it has 8 electrons around it. But because of the covalent bonds, these 8 electrons are supplemented by 1 from each of this hydrogen, so there's actually 10 electrons in this region with 8 protons. This means that this side of the water molecule has a slight negative charge. On the other hand, these hydrogen atoms the hydrogen atom is just a single proton, and the electron is being pulled a bit in this direction, which means that this side of the water molecule tends to have a slight positive charge. Slight charges, separated, dipole. So an electric field can create a dipole moment, but an electric field can also affect a dipole object. Most simply, if there is an electric field, an external electric field, around a dipole object, the positive charge will experience a force in the direction of the electric field, and the negative charge will experience a force in the opposite direction of the electric field. If the dipole moment is not pointed in the same direction as the electric field, this can cause a torque or a twist on the dipole moment. The quantity of, or the magnitude of this torque, or the value of this torque, is given by P cross E, cross product, dipole moment, direction of electric field. If the dipole moment is pointed in the direction of the electric field, there is no torque. And if it's pointed in the opposite direction of the electric field, there is no torque, but it is an unstable system. Now this is true for any electric field. If the electric field is non-uniform, we can also get a force. So consider the following. First, a dipole is made of two charges, one positive, one negative, separated by a slight distance. Second, at two different points, the electric field will be different. And the difference between these 2 points on the electric field, assuming that d is really small, can be given by this formula right here. Now, please note, this is not a divergence or a gradient or any of the other del products we've seen before. Specifically, we need to do this multiplication first, but following the order of operations. So this quantity right here is dx times ddx plus dy times ddy plus dz times ddz. Let me write that out for you. Which means that you'll take this derivative on E and multiply it by the x component of D. Now, if the electric field is different in each region, or at each point, then both points will not experience equal and opposite forces. There will be a slight difference in the magnitude of those forces, which means the net force on the dipole object as a whole is equal to the charge times that difference in electric fields. We consider that Q is a scalar, which means it can be stuck anywhere in this equation. If we stick it right here, QD, that becomes the dipole moment. We can say that the total force acting on the dipole is equal to P dot del times the electric field.